This is 3.6 rational functions. We've been talking plenty about the domain and the range, but let's focus on, we've said this before, but the domain is basically all the numbers that can fit in there into the function that works, but you always got to keep in mind what x cannot equal. So specifically, if the denominator is 0. So, and what that's going to happen when you graph it, because x, you cannot have a 0 on the denominator, so that's going to make, when you graph it, it's going to make an asymptote. So it's like an invisible line, whether a vertical line or a horizontal line, that the function will not actually hit at that spot. So let's consider a very basic parent function. Let's consider this right here, f of x equals 1 over x. Now, when you start making, well, first of all, you should notice x cannot equal 0. I mean, you can't have 0 on the bottom. So when you start making an XY chart, we typically plug in nice numbers like 1, and then 1 divided by 1 is 1. Plug in 2, and that becomes 1/2. Plug in 3, and that becomes 1/3. And you might even plug in -1, and that becomes -1, -2, and that's -1/2. And then you start graphing this, and you start noticing what's happening as the function, as you plug in 1, 2, 3, 4, and -1, -2, -3, -4. As you start looking at that function, you'll notice that it keeps getting really tiny. So even at 2, it's at 1/2, and at 3, it's 1/3. At 4, it's 1/4. So notice it's getting lower and lower and lower and lower. And the same thing on if you start plugging in -1, you get -1. When you plug in -2, you get -1/2 and -1/3, -1/4. Notice it's getting lower and lower and lower and lower and lower and lower. And so what we want to consider is what happens to the graph when it approaches, like x cannot equal 0. So imagine what happens, and this is what I said, consider x as it approaches infinity. Okay, that's something you should, like if I get really high, x equals 10, 20, 30, 40, what's happening to the function? And then also, what happens when it approaches the asymptote? So the asymptote, again, in this case, x is what x cannot equal. So what happens if I plug in numbers, like I know 1, 1 is right there, but what happens when I plug in 1/2? When I plug in 1/2, or when I plug in 1/2, I'm going to get 2. So plug in 1/2, you get 2. What happens when I plug in 1/3? Or 1/4, or 1, I get smaller and smaller, so 1/4 and 1/10 and 1/100th. And what happens as I get tinier and tinier, closer to 0, closer and closer to 0, what's happening to that function? So even like 1/4, I'm going to get 4. 1/10, I'm going to get 10. 1/100, I'm going to get 100. So notice, as I get really, really close to 0, it's getting really, really, really high way up here. So this function, you can see, it's going to look like this. Now this never hits 0, okay? It gets closer and closer, but it never hits. The same here, it gets closer and closer and closer, but it will never hit that line, no matter how big we go. As x gets closer and closer, you'll see that it never hits that x line. Well, the same thing down here. As I keep going closer and closer and closer, it never hits that x line, but it gets very close to it. Start plugging in like -100, -1000. Where is the function at? When I go, as x gets closer and closer to negative infinity, where's the function? And as x gets, again, if I plug in -1/2 and -1/4 and notice it's going to get tinier and tinier and tinier. So as x gets closer and closer to 0 from the negative side, it just keeps going lower and lower down. So same thing here. So -1/100. So you're going to get -100. And so you'll see that this is the parent function, and notice the asymptote, you actually have a vertical asymptote and a horizontal asymptote there because it never crosses there. So if I drew it in green, so there's like an asymptote right here. It's like an invisible line, and the same thing with the horizontal line at x equals 0. So, or y equals 0. So you notice that we have to consider as x approaches infinity and negative infinity and the asymptotes, what's actually happening to the graph. So let's look at graphing another problem, but notice we want to also state the domain and the range. So notice on this function, the parent function, keep in mind the parent function is 1 over x, okay? So if you remember we just graphed it, so the 1 over x, what it's going to look like. But notice this right here is being shifted 3 spaces to the right, and notice that x cannot equal 3, cannot equal 3. So that automatically tells me I have a vertical asymptote at x equals 3, and notice that I have a horizontal asymptote still here. So notice it's the same parent function, it's being shifted over. So if you needed to, you can start plugging in numbers, but notice the asymptotes. So as I plug in numbers close to 3, so if I plug in 4, what's happening to that function? So you're going to end up getting, so 2 over 4 minus 3, so you're going to end up getting 2. So at 4, 2. But notice as I plug in 5, as I plug in 6, well, what happens if I plug in numbers like 3.5, 3.3, 3.1, 3.01? I mean, what's happening to that function? And you can see that it's going to get closer and closer and closer to that asymptote. And the same thing here, it's going to get closer and closer and closer to that 0 mark right there. It's never going to reach it. So the function is going to look like this. And the same thing if I plug in numbers close to look at the asymptote, okay? So look at the other side of the asymptote. So as x is getting to 1, 2, 2.5, 2.6, as it's getting closer, what's happening to the function? So notice it's going to get closer and closer and closer and closer this way, and it's going to start bending and getting closer and closer. So the function is going to look like this. The asymptote is the important thing. So notice the domain and range, by the way, x can be anything, okay? X can be anything. So except the domain is, all the real numbers. So x is all numbers such that x cannot equal 3. And then the same thing with the range, the y can be anything except it cannot equal 0. So let's look at another scenario. So here you have the same type of thing, graph it and state the domain. Well, notice the very, very first thing you should notice, x cannot equal -2. So I automatically know there's a vertical asymptote x equals -2. Also, if you actually divided this, because that's what that says, it's division. So if you actually take 3x plus 5 and you divide it by x plus 2, you'll notice that you get 3. And then if you kept dividing, so that's 3x plus 6. Subtracting that. So we're going to get 3 and then plus a -1 over x plus 2. Now what that means is at 3, so at 3, so that literally tells me there's a horizontal asymptote at 3, and you're literally going to be minusing that from that. So that tells me there's a horizontal asymptote, and then I just have to graph it. And again, this is from the parent function. So you're literally going to be graphing it, and always pay attention to the x. As x gets closer, look at this right here, the vertical asymptote. So as x gets closer to -2, so -3, -4, -5, and then consider it as -2.5, -2.2. What's happening to the function? And then the other side of the asymptote, so -1. This is the other side of the asymptote. So -1, 0, 1, 2. As it's getting, further away from it, what's happening? And then again, the same thing. What if it's really close to it? So -2.5, -2.6, or -1.5, -1.6. So as you get closer and closer, what's actually happening to that function? And you'll see that the function looks like this. So again, it keeps getting closer and closer to that asymptote, but never reaches it. It keeps getting lower and lower to y equals 3, but never reaches it. And the same thing here, as I plug numbers in, it's going to get closer and closer to the asymptote, get closer and closer to y equals 3 to be able to do that. And again, the domain and the range, the domain is all numbers except x cannot equal -2. And the range is all the y numbers except y cannot equal 3. So finding the asymptotes is important because you can see what the function is going to look like. So a little bit bigger problem. Notice here we have a bigger polynomial divided by a bigger polynomial. And then notice right at the denominator, look at the same thing again. The denominator, you cannot have 1. So I know there's a vertical asymptote at 1. We'll use different colors. So at 1, there's a vertical asymptote. And again, if you do the long division, as we did prior, notice that you're going to have a horizontal asymptote. You're going to have a horizontal asymptote at 2. If you did the long division, you'll see that the first term is 2, and you'll be able to see that. And then again, you notice you just start plugging in numbers close to this. As x is getting, as x is, you can't equal 1, so try 1.1 and try 1.5 and 2 and 3. And notice what's happening to the function as you plug in numbers to that function, what's happening to that function when you start graphing it. And then the same thing as you get, that's 1.1. So as you start graphing this, it's going to look like this. As x gets further and further away from the asymptote 1, and as it gets closer and closer to 1, like 1.01, you'll see it's getting very high. 1.001 is getting very, very high. And the same thing if you start plugging in numbers on the other side of the asymptote, like 0 and even 0.5 and 0.6 and 0.7. Notice I'm getting closer and closer to the asymptote, and you can even get further away from the asymptote, -1, -2, -3, and find out what's happening on that side of it, and you'll see that the function looks like this. So again, you have to evaluate where the asymptote is and consider what's happening to the left of it, what's happening to the right of it, and the horizontal asymptote is important too, because how low does that go? And then, of course, then we can talk about the domain and the range as well. So the domain is all the real numbers, except x cannot equal 1. And the range is all the numbers except y cannot equal 2. So let's look at how to find the asymptotes. And so there's some of the ways that we can do this is, notice the vertical asymptotes are where x equals a. So we've been doing that. You look at the denominator, it can't have 0 in the denominator. That's a big, big clue. So that's how you find the vertical asymptote. Now, how do you find the horizontal asymptote? Well, if n is less than m, so if you look at the exponent, the leading coefficient, exponents, the leading exponents, so if n is less than m, so an example of this would be like if I had x squared over x cubed. See, if n is less than m. So then R has a horizontal asymptote at y equals 0. So we just got done graphing one of those. If you go back and look at it, the y equals 0, if this is the y line, the x line, and the y line, so y equals 0 would literally be right on there. And that's what we did at the very beginning. So if n is less than m, and an example, we had the 1 over x. Okay, so that's where the horizontal asymptote was at y equals 0. So if n equals m, so an example of this is like if I had x squared plus 3x plus 9 over x squared minus 8x plus 7, something like that. Notice the n and m equal each other. Then notice the horizontal asymptote is a divided by b. So if you notice the a and b that I have here. So in this particular example, 1 divided by 1, so the horizontal asymptote would be at 1. If this was 4 divided by -3 or something like that, so then it would be at -4/3. So you basically have to look at the coefficients if the exponents are equal to one another. And then finally, if n is bigger than m, so an example of this is x cubed over x squared, then there is no horizontal asymptote. So that helps you out a lot. If you go back and rework those problems with this principle in mind, you don't really have to do the long division that I did earlier, and you just have to keep these principles in mind, and that will help you find the horizontal asymptote. This is part 1 of 3.6. You'll need to finish watching part 2 to get the rest of this.